Hello, everyone. My name is Elisa Baum, and I'm GridGain's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of housekeeping. First, if you could please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me. And let me take a look. I see hands. Thank you very much, everyone. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. In addition, a recording of this webinar will be made available to everyone within 48 hours. I would like to thank you for attending today's webinar, Turbocharge Your SQL Queries in Memory with Apache Ignite. It's being presented by GridGain founder and CTO Nikita Ivanov. And with that said, I will turn the floor over to Nikita. Go ahead.
Thanks, Elisa. Good morning, everybody, or good afternoon, depending where you're joining from. What we're going to be talking today is what Elisa just said. We're going to be talking about how you could turbocharge your SQL queries in memory using Apache Ignite. So we'll talk a little bit about Apache Ignite, but we're not going to do the full-blown presentation about it. We're going to concentrate on a data grid. And a data grid is a component that actually hosts the SQL capabilities of it. And we'll talk in details, in depth about what and how we implement SQL capabilities in Apache Ignite. In last maybe 15 minutes, maybe 10 minutes, I'll show a pretty cool demo. We'll basically run Spark SQL and Ignite SQL on exactly the same data set from a Apache Zeppelin, which is the very nice kind of notebook interface, and we will see the performance difference between the two. So. Let's talk about just briefly what is Apache Ignite. And again, I'll be very quick here if you guys are interested in a lot more about Apache Ignite and all the different capabilities, because it's dramatically more than just a SQL end. You guys can look at an Apache Ignite website and just or GridGain.com website and get all the information. But in a nutshell, Apache Ignite is what we call in-memory data fabric. It is a distributed Java-based middleware infrastructure software that architecturally slides in between your traditional data sources, your databases, your file system, your HDFS, whatever you have, on the bottom, and your applications on top. So it slides in the middle, and it provides you fundamentally speed and scale. It provides you speed by moving data from the slow disk and flash-based devices to RAM across distributed computers, and provides you essentially scale by massive distribution and parallelization of a processing of this data. So we call it a fabric for a reason. It has many components with which you can process and store that data in RAM across multiple computers. We have a data grade and streaming grades and compute grade. We have a Hadoop and Spark acceleration. We have many components in this fabric. And again, fundamentally in-memory data fabric, which is Apache Ignite, is all about speed and scale. It's always kind of interesting, I understand that in-memory is not just about a marginal speed increase. And when I present about the subject, I always keep saying, if you're looking for just a 2 or 3 times performance increase, you can just go with a flash. Move your data from spinning disk or spinning rust, as we call them, to flash, and you get a sizable increase, 2, 3, 4 times. In-memory systems, and Apache, one of them, can give you a several orders of magnitude performance increase. You can go anywhere between 10 to 1,000 times faster than a traditional disk-based systems. We actually, one of the prime examples I always give about performance of a memory system, not related to Apache Ignite specifically, but about in-memory systems. A couple of years ago, we achieved a billion transactions per second. I'm talking about a fully ACID normal transactions per second on 10 commodity blades, with total capacity about 1 terabyte. So that's what in-memory systems can do for you, in specifically Apache Ignite. Just a quick history about a project. I think maybe some of you heard about GridGain project, and essentially GridGain was a kind of precursor to Apache Ignite. And GridGain project was started by by me and my co-founder around about 10 years ago in 25. In 27, we have a first public release, and from that point on, the project grew and grew, and a couple of years later, we had a pretty large production installation with over 2,000 physical nodes. In 2010, we started the company GridGain Systems around this project, and the project grew and grew in popularity. Today, it actually starts almost every second around the globe. In 2014, we've been always open source project, by the way. We've been always open source company, but in 2014, we decided to not only have the license, Apache license, but we decided to join ASF, Apache Software Foundation, and we were accepted in incubation. And in 2015, last year, we were graduated to the top level project in Apache Software Foundation. One of the fastest projects. I think we're just the second project behind Spark in terms of the speed of graduation. It's still to this day, it's about the only in-memory data fabric that is a top level project in Apache Ignite. So what's really interesting about the Apache Ignite, although it's a fairly new project in the Apache ecosystem, it's extremely mature code base. We have hundreds and hundreds of production installations around the globe. The code has been in production for almost 7 to 8 years by now. So it is extremely mature code based and very mature project overall. So as I mentioned to you a couple of slides before, it's a fabric, and it's a fabric of many, many different components. But we'll talk about the SQL today. And SQL is essentially a fundamental part of what we'll call a data grid. So we'll talk about data grid, what it is, and we'll then basically dive into the SQL capabilities of what we do. So what is a data grid? And it's kind of important to understand what it is, to understand what is SQL. What does SQL mean in terms of the in-memory data grids, because that's a part of it. So we'll talk about memory data grid first. So what is in-memory data grid? The very simple idea behind a memory data grid as a component, essentially imagine this. Imagine you have a terabyte of data that you want to store in memory across multiple computers. Essentially, you cannot feed all the terabyte into the one computer's RAM. You have to spread it over multiple computers. And when you have to do that, you essentially open a whole can of worms. How do you partition? How do you load balance? How do you transact? How do you query? How do you ensure availability? What happens if one node dies? How do you ensure all of these different semantics about storing data? That's essentially what data grids do for you. They provide you a fairly simple interface, how to interact with it. You can basically put data in, get data out, query this data, and data grids manage everything else under the hood. Fundamentally, most of the memory data grids, and Apache Ignite's data grid is not an exception, are based on a key value store, in-memory distributed key value store. It's a very important fact. The reason that we chose the key value, because this is the lowest common denominator in terms of the data storage. Once you have a key value store, you can then look at the same key value store as a SQL store. You can look at the same data as the file system. You can look at the same data as MapReduce type of jobs on top of it. So the key value is very fundamental because it gives you ability to look at this data, essentially providing you a view on this data from a very different perspective. And that's exactly what we do, by the way, with SQL. So we're based on distributed memory key value store. The data in data grid can be traditionally stored in two major ways. It's a replicated way and a partition way, and I'll explain very quickly. In replicated way, each node in data grid would have exactly the same data set. Essentially, you obviously limiting the entire capacity by the size of a single node. On the flip side of that, you get a tremendous high availability because you can ping any node in the cluster. It will have exactly the same data set. So for the read mostly systems, this is the best way. Naturally, for the write mostly, it's pretty bad way. It's pretty inefficient way because you have to update all the nodes on updates. Partition is probably the main mode for data grids, is where you are actually partitioning data, and each node in the cluster stores only a portion of the data. There's a plenty of configuration settings. There's plenty of caveats on how do you do and what not to do. But fundamentally, there's just two modes. And they're kind of important for understanding how SQL works as well, especially when we talk about distributed joins, by the way, and we'll come back to this later. So naturally, data grades are good for terabytes of data. I don't think data grades and memory data grades are good for gigabytes. You can store gigabyte in your iPhone. It's not really good for the petabytes yet. It's just not economical. It's hard to scale in memory systems to the petabyte scale. So in-memory data grades are an excellent choice for a lower teens of terabytes. When you have half a terabyte, 5, 10, 20 terabytes, that's where I see the most of the value. As you go up, it becomes pretty problematic economically to do that. Memory is still somewhat more expensive than flash. What we also do in our data grade, which is fairly unique in the sense, is that we support both on-heap and off-heap RAM. It's very, very important, especially nowadays. If you guys work in the Java world, you guys know the maximum that on-heap can support before the garbage collection starts killing you, somewhere around 6 to 8 gigabytes. So if you have a box with 96 gigabyte of RAM, you have to have the ability to use that. And Apache Ignite has a tremendous capabilities to essentially completely seamlessly use both on-heap and off-heap RAM. You don't really know what's going on. You basically just enable that, and it's just going to use the entire physical RAM available on the box. So we have essentially high availability for in-memory replicas and automatic failover. Those are very traditional things. I'm not going to spend too much time on this. What's interesting, we have a full distributed asset transactions. It's a very important feature. It's one of the most differentiating features that we have in our data grade, apart from a very strong SQL support. We have exactly the same transactional support, which, by the way, dovetails to the SQL level, but we have exactly the same transactional support as would normal database would have. We have both pessimistic and optimistic transactions. We have all the same isolation level for Java transactions like read committed, read down committed, and even serializable. So if you guys work with transactions in database, you can work exactly the same way with Apache Ignite. The same guarantees, same semantics. We are participating in other transactions, so if you want to span transactions from a memory to database to JMS, for example, you can do that. We can participate in normal GTS, GTA transactions in Java world. So without further ado, we have SQL and JDBC drivers. As a matter of fact, we're coming up with the ODBC driver as well. So as we transition into the SQL conversation, it's very important to know that you can literally just open JDBC driver and soon enough ODBC driver from a non-Java environment and just literally connect to the Ignite and just use any other tools that actually work over JDBC or ODBC to query the data. For example, if you guys work with Tableau works over ODBC, you can connect Tableau to Ignite and just visualize the data from Ignite. Same goes with JDBC as well. So this is kind of very, very quickly just a brief introduction to in-memory data grid, because the SQL is the fundamental part of a data grid. How? It's actually very interesting. I get this question even to this date. I get this question: why do we need SQL if we have a key value store? It's very interesting because originally data grids never had SQL, and some of the data grids today, like Coherence, for example, from Oracle, doesn't really have a SQL either. And my answer to this is very simple. If you have a key value store, in order to get data out, you have to have a key. If you don't have a key, you're out of luck. You have to do the full scan. And the fundamental property of SQL is an indexing support. And you can actually run a very effective queries where you don't have a specific key. Imagine you have a large data set and you want to say, hey, it's a very simple data set of employees in the companies, right? And you want to say, what, find me all employees that start with has first name Nikita. And if you don't have a normal SQL with the full indices support and whatnot, you have to do full scan. You have to scan the entire data set with the predicate and basically look for the first name, right? In SQL allows you to do extremely effectively. You can index this, field properly, and you can select with a where class. It will be instantaneous response. That's the part of a SQL. I know it's kind of obvious for most of you probably, but in a world of in-memory data grids, that's not it. Not every project would have it, and as a matter of fact, only few. And I would claim that Apache Ignite has the best SQL support, and we'll talk about it, why I'm saying this. So first of all, what do we have? We have a full ANSI 99 SQL. There is no gimmicks. There's no custom things. If you know SQL and especially NC99, you know how to use Ignite. Period, full stop. There's nothing specific, custom, proprietary here. It's a full normal standard. It's actually very important. And that's the essentially a side effect of how we decided to implement that particular feature. Unlike almost anybody else in kind of between our friends and competitors, we decided not to implement our entire SQL engine by ourselves. It's a very hard job. It took Oracle 25 years to get fully optimized SQL engine with query planning and optimization and everything else. So what we decided to do, we decided to take the H2 engine, which is one of the best local SQL engine available today, which is open source and free, and we have the H2 engine on each node in the cluster. And the only thing that we do at Apache Ignite, we provide all the distribution and distributed logic and how do we basically do this distributed SQL. So that actually allows to have an extremely well-tested and well-maintained H2 execution engine locally in each node. And that's basically where this NC99 standard support comes from, and that's where the speed of the local execution and local query planning comes from. It's dealt with H2. And only thing that we do, which is, in retrospect, fairly large thing to do and fairly complex thing to do, but the only thing we do is we provide this distribution and distributed logic for the SQL processing. That's a very, very, very important point because we just seen how many are our friends and community struggling with the SQL performance, anywhere from Spark to all of the data grids that basically trying to implement their own SQL support. And I think our design decision early on has been spot on because we are an absolute holding record in terms of SQL performance in our project, and I'll show it to you. So we're shipping with GDBC drivers soon enough. I think literally in the next point release for Apache Ignite, you guys can look at the dev list. I think it's been already developed. It's just a matter of releasing it. We're going to have ODBC drivers as well. So essentially, the entire ecosystem of connectivity to our system from the outside for the SQL will be covered from GDBC and ODBC as well. Another interesting feature we have is the power change tolerance. That's actually fairly kind of deep technical question, but fairly important. The minute you have more than one node, let's say traditionally in our clusters, clients would have 10, 15, 20, 30, sometimes hundreds of nodes. The nodes have a tendency to go up and down. You either add nodes to the cluster at runtime to kind of scale out, or your nodes is crashed, or you're doing the development, during the testing. Something is happening, not constantly, but in the large clusters, that's not something you can ignore. So when you query the data, you have to be guaranteed that in any given point of time, no matter how many nodes often up and down or starting or stopping, you're querying a consistent set of data. It's easy to say, it's much harder to do, but we do have a topology change tolerance. So you can be querying data with SQL, and you can add nodes, you can remove nodes, and we're always going to give you either an exception back, say, hey, we cannot really query the data because literally the cluster is in stable condition, or we're always going to give you the result from a stable data set. We will never give you the incorrect result, let's say incomplete result, because some of the data was in transit between the nodes and whatnot. It's a very important consideration. It's actually a very nice feature that you don't have to literally reinvent the wheel how to support this type of functionality. So we have InMemory Indices. As a matter of fact, we have pluggable indices in our project. It's one of the only implementation that I know of where you can actually plug your own index. Obviously we support primary and secondary indices and whatnot. You can plug your own indices. If you fancy some kind of Bloom-based indices, you want to develop them, fine. We have this little interface. You implement interface, plug it in, and you can use this index right in your SQL definitions. It's a very, very advanced feature. Not everybody would use it. You gotta be, you gotta know what you're doing when you develop your indices. But guess what? If you have something very specific you want to do for the optimization, fine, you can develop that. Naturally, since we support on-heap and off-heap in our project, we do support storing indices both on heap and off heap. Very nice feature. So as we are distributed systems or system, we support distributed our SQL aggregated functions like group by, aggregations, and sorting. Kind of goes without saying, it's natural, but we do have that, and that actually helps the performance quite a bit. You know, we gain performance by parallelizing SQL, and naturally it sounds simple, but believe me, implementation of that is fairly non-trivial to do that. The next point is kind of very important. We support a distributed cross joins on different cache and joins and unions as well. As if you guys know a little bit of a theory behind SQL, the joins don't really work very well in a general sense in distributed systems because you have the explosion of keys exchange. For you to do, basically to do distributed joins, each and every node has to exchange a dramatic amount of keys, if not all the keys in some cases, and that's hard to do. So naturally, there's a multiple ways to do that. One of the ways that we support almost automatically is what we call a star schema, is when you keep your dimensions in the replicated cache and you keep your values in the partition cache. Remember this replicated and partitioned? So if you can do that, and if you can basically store your data in this way, you can do extremely efficient distributed joins in SQL that will actually perform extremely well. Naturally, you can join multiple caches, and think about cache as a table. It's kind of synonymous. Cache in the memory system kind of equals to a table in the SQL databases. So naturally, we can do the cross cache joins between multiple tables. And if you do them in the star schema, again, dimensions in the bucket cache and values in a partition cache, we can do these joins extremely efficiently. But there is no ways to kind of change the laws of physics. If you don't do that, and you have terabytes of data, your distributed joins will be slow, no matter what. They'll be slow in many systems today. Another interesting thing, we support ad hoc SQL. So sounds like a normal thing. You'll be surprised. In some of the in-memory systems, like kind of escaping me, some of the databases that we in-memory databases, you have to know your SQL queries up front, and based on those queries, the system will do the data allocations. That's not the case for us. We don't have that limitation. We support full natural SQL. Whatever you want to write, it's a completely ad hoc SQL. Another feature I want to talk about is, and by the way, we're going to stay on this slide for quite a while. This is the kind of main slide we talk here. Another, basically, one of the greatest features we have in our SQL support is a custom SQL functions. I cannot emphasize enough how important it is to really, for the real life use cases in SQL. So we do not have a store procedures in our support because store procedures are always specific to any database, right? And we literally don't have store procedures. You don't really have to have them because you work in a Java environment. To kind of mitigate that, we have ability to write custom SQL functions in whatever language you want. In any JVM language, use Java, Scala, Groovy, whatever you like, you can literally write a function and use that function in your SQL queries. So that's a tremendous capability to basically inject whatever logic you have. And believe me, this function can be whatever. This function can essentially do a custom MapReduce job or write from a SQL. Now think about it again. You can have a complex SQL query with the joins and whatnot, and right in that SQL query, you can invoke a complex, for example, MapReduce function or distributed kind of NDP type of processing. It's a very powerful paradigm. And it's very easy to do, and it basically makes our SQL capability extremely powerful. You're not only limited by what SQL provides you, those are very basic functions. You can essentially do whatever, frankly, you like to do in your SQL. Pretty cool stuff. We have a GUI-based schema import. Essentially, if you have an existing database and you want to import this database into the in-memory, we have a very nice GUI-based tool that will read this database, will create the schema for you, create the Java objects. So basically, it will do all the dirty work for you on how to basically import this data effectively and cleanly from database. We're going to spit out a bunch of Java classes. You can take it off and do whatever you like with them, change them, or add some functionality to it. But we're going to do all this kind of, boring, error-prone work for you. We're going to scan the database, create the Java definitions, and everything else. So great start, by the way. It really cuts down, hours, sometimes days of work into literally half an hour. Run the tool, get your stuff in, look at it, change here and there, and boom, you have ready. You can basically import the data from your database into the in-memory system. Very, very nice tool. We also support dynamic schema change. It's actually a pretty complex subject, by the way. It kind of dovetails into another feature that we have in our project, which is essentially called, we call it basically it's dynamic objects or a cross-platform objects, is where you can store data, let's say from a .NET, and then read this data from a Java side. And we're going to properly convert all the types properly. So you literally store .NET object in a cache, and you can read it as Java object, or you can read it as C-level object. And we're going to properly convert all those types. So part of this is, essentially those objects, you can think of them as kind of JSON-based objects, although the format as a binary is much more optimized. But that gives ability to have support for dynamic schema change if we need to. We can add fields to it and remove it. We have geospatial indices as well. So if you are into this realm of processing, we support geospatial indices. So you can basically use this functionality. Another feature about support of Lucene and predicate queries, it's a little bit kind of, a parallel to this, but in exactly the same functional area where we actually have SQL support, we also support a Lucene text queries and basic predicate queries. So if you want to do a full scan on predicate, be my guest and scan the whole thing with the predicate. We also have fairly optimized Lucene text queries. So if you're just looking for a text searching, right, a Lucene-based search, we support that as well. So as a matter of fact, uncollocated join support is something we already, I think, introduced. I'm not sure if it was released with Apache, but it's literally done, and it's either audio release. You guys can grab it in our latest, nightly build and have it, or it will be released in, I think, in 1.6 Apache Ignite. Again, it's an improvement in our join support. You don't have to collocate any more data for it to work. It's just going to work, but slowly. At the point right now, it doesn't work, so it will basically not work if you don't have a collocations. With this new capability, you do not have to collocate. It's just going to work slowly, but it's still going to work. So that's the interesting thing. And we also working very, very strong. And it's a part of a community work, and part of what we do at GridGain as well is we're going to support more and more with disk storage capabilities for the use cases where you cannot fit everything in RAM. And today there's one limitation on the project is that if for your SQL queries to work in a proper way, all the data has to be in RAM. And there's a certain limitation to that because there are use cases where you cannot fit all of this in RAM. You literally, have terabytes and terabytes of data, just maybe impractical for you. So for those use cases, we're working pretty hard on supporting a kind of what we call a hybrid storage model where the data can be stored in RAM and multiple types of RAM and on flash and on disk, and your queries, including SQL queries, will work transparently over all of these different mediums. That's coming up very shortly, probably by early summer. So literally we're talking about a couple of months away. We're going to have that support as well. So this is basically, again, briefly, but kind of bulk of the features we have in the SQL support. As you can see, we pay a lot of attention to the SQL stuff, and naturally, when it comes to SQL, there's literally just a few important factors. I mean, what kind of SQL we support? We support ANSI 99 standard. Is there any limitation? There are some, but very few. And speed. And speed is pretty much paramount. Speed has to be one of the top concerns. I'm going to show it to you in a second. But let me show you some very brief examples. This is basically just literally, I believe it's a Java code. And that's basically how simply you can use it from a Java application. So literally, just get the Ignite cache, which is, think about it as, just a table or basically in a SQL speak, it's like a table. And then once you have a cache, you can create a query as simple as this. Is a simple query. There's no gimmicks. It's literally just a simple normal SQL query. You can use any type of SQL in it, and you get a nice distributed cursor back with the result set, and then you can print out your things. So there's a lot of machinery here, by the way. You can literally query terabytes of data. Obviously, we're going to do it distributed fashion. We're going to only pull the data that's necessary for a particular cursor asynchronously for you. So you can literally iterate over terabytes of data very nicely. And this is another basically joined example. Again, very, very simple. Again, you get the cache, you create the query, you execute the query. Simple as this. And if you know results very small, you can say get all and basically have a nice data set or result set back. So, by the way, this is a group by example too. So here's what I'm going to show you. We have about we have a good half an hour. So let me go and spend maybe 10-15 minutes on the demo, and I want to leave about 10 minutes for the Q&A if you have any questions. So the demo I'm going to show you is pretty interesting. So we thought about how can we demonstrate the speed, because speed has to be somehow competitive. So we picked a pretty good project in our friends in Spark community. So what we're going to do, we have a data set. I'm going to show you a data set. And what we're going to do, we're going to start the Spark cluster, and we're going to start the Ignite cluster. And then we're going to use exactly the same interface, which is Zeppelin. And Zeppelin is very nice in notebook style interface. If you guys haven't looked at it, I highly recommend. It's pretty cool stuff. It has both integration with Spark and Apache Ignite. So it's very unbiased. And we're going to use exactly the same SQL queries to run against exactly the same data set, but the data set will be loaded in Apache Ignite, in Apache Spark, and we're going to see the performance. So let me kind of walk you through some of the setups here. I'm going to get out of this presentation slide deck, and what I'm going to show you first is where to get this demo. The demo is completely open source. It's on the GitHub. And by the way, when you get the slide, on the last slide on the slide deck, you're going to see exactly this URL over here. So don't worry if you don't catch it right now. It's all on GitHub. It's all free. It has a very detailed documentation how to do it. It's very simple. Literally, the entire documentation is basically like this. It takes you about 5 minutes to set up. Everything is pre-built and everything is ready. So you can basically replicate this entire demo very easily in about 15 minutes, from scratch. If you're interested, you can play with this. So what I've done basically is we have a Spark cluster, and it's right here. Hopefully, you guys, I kind of blow up the phone, so I hope you guys can see that. So it's a 106 Spark. It's running one node over here, one working node. And what I also done is I started 2 nodes on Apache Ignite. And I've started them basically when you download the Zeppelin demo. Essentially, you get a very nice Maven-based project, and you can basically just click on this node file, and it will run this on any IDE, Eclipse or IDE, and you can basically start 2 nodes. So you can see that we have 2 nodes in Apache Ignite, and we can confirm that they actually have a 2 servers. So essentially, we have 2 nodes. Now, in terms of the data set, there is a little program here that actually generates data set for you. And let me see if I can actually show you a little bit better in the presentation mode. So if you look at over here, essentially it's a very, very simple program that basically generates 2 JSON files. And those JSON files is exactly what gets loaded into the Apache Spark or into the Apache Ignite. So we have a very simple structure here. It's organization persons within organizations. We have 500 organizations, and we have 1,000 persons per organization. So it's a small data set, something we can test and play pretty quickly and easily. And we basically generate 2 JSON files, organization JSON and person JSON. This is a very simple program right here. So I'm going to show you the files. I already pre-generated them, so we don't spend time right now. So if you look at here, I'm not sure you can see, but we have the two JSON files here. We can actually open this JSON file. We can take a look at it. So this is the organization. It's pretty boring, nothing there, and this is the person file. And let me just open it. Oh, it's too big. All right, fair enough. So we can open it a little bit differently, I guess. So when we have the persons file that contains about 500,000 persons, so pretty simple data set. So let's go back to Zeppelin. So this is basically a Zeppelin interface. If you're not familiar with it, I'll give you a very, very quick overview. It's very simple, by the way. It's basically have notebook style interface to a data set. So if we have two notebooks, Ignite Demo and Spark Demo. So if you open the Spark Demo, for example, this is essentially what you do. You basically can write a SQL or a Scala code right there, click run, and it executes it for you. You can basically see results. It's a very nice, very productive, kind of analytics, data analytics interface. By the way, Databricks, if you're familiar with the Databricks analytical suite, is very much look like this. So it's a pretty popular concept. So here's what we did for a Spark demo. In Spark demo, essentially, you need to do a little bit of a prep work because you need to load those JSON files into the Spark. And that's what we did here. I already did that, so we don't have to spend time. It's very simple. You just SQL context and read in JSON. You could do this for the organizations, and you do this for the person JSON. So those you basically create those data frames in Spark. And once you've done that, you register a table, basically a linked data frame with a table through this command. Once you've done that, you're all ready. So now basically you can start querying SQL, using SQL to query this data. So once again, just to again reiterate, we have one node in Spark and one worker and one master. And here on the Ignite side, we just started those nodes right from the IDE, literally from the code. Doesn't really matter where they are. We just start them right here. So we can go back in our Zeppelin notebook. Let's execute this. So essentially, this is our SQL right here. Again, we can copy this SQL right from the GitHub page, so we don't have to type all of this. So I essentially just copied this, and we can play with all of this as much as we like. So I copied this over here, and we can just click Run. And it's running right now. As you can see, basically, that's what's happening with the Spark. This is the running SQL against Spark. So it gave us all the results, and it took about 8 seconds to do that. So now we can go back to a different notebook, which is Ignite notebook, and literally I already copied again, but the only difference here is literally this. So you have to let Zeppelin know that you essentially running a different interpreter. One was for the Spark, and this one is for Ignite. The data set is exactly the same as with Spark. It's exactly the same two JSON files we loaded up. We loaded up them in the Spark cluster. We loaded up on the Ignite cluster. I'm sorry. So now right here we're going to be querying data from Ignite cluster. Very much the same interface. Again, we just click Run, and we got results. Now notice the difference. Now this is what's really striking here. It actually shows 0 seconds, but believe me, the Zeppelin doesn't really show you the milliseconds. So if you really query this in your applications or somewhere you can actually get down to the millisecond level, you will notice that Ignite performance is about 100 times, 2 orders of magnitude faster than a Spark SQL. And the reason for that is not that we are smarter than Spark folks, absolutely not. Spark is an awesome project. But the Spark SQL does not really have indices. Indices is very hard to do for RDDs, which is the resilient distributed data sets, the concept that is, Spark is based on. It's very hard to do proper indices there, and the Spark SQL still doesn't have, a proper indices at all. So naturally, in a Spark SQL, almost every query is the full scan. And even for a small microscopic data set as we have today, literally, 500 organizations and thousands of people per organization, something you can do on your iPhone very easily. Even on this small data set, the difference is noticeable. Imagine you do this on your streaming pipeline or any kind of processing you do. The difference between 8 seconds and literally 8 milliseconds is quite dramatic. And again, we'll prove it again. So you can go back and play with the Spark. As a matter of fact, let's just clean up the output. And let's pick up something else here from a different query. We can pick up this query. Let's say second one. We can literally run again here. And it's a simple join with the group by, and it's, it's going. So as you can see, that's a little bit more involved than the previous query, but it will be done. So it took about 20 seconds, and it took about 20 seconds, and let's go ahead and try. So I don't have to type this whole thing. I just copy it over from here. We go back to Ignite Notebook. Let's just clean this output so we don't have it, and let's just paste it again here and run it. Now notice the result here. As you can see, there's absolutely no slowdown, right? As a matter of fact, the difference here is much more dramatic than the difference in the previous example. The difference here is probably almost close to 3 orders of magnitude. Not exactly, but you guys can test it out properly with a proper instrumentation to see exact numbers. But the difference here is quite dramatic. You can probably see it visually. One thing took 20 seconds to process, which is very, very slow. You can visually see this. This one took nothing. You press the button, you get results. It's instantaneous. It's exactly the same data set. It's exactly the same SQL query. That's the part of what we do in Apache Ignite. And again, not to brag too much, but we do quite a lot in optimization for what we do in SQL, right? Remember, we use H2 locally, so that we use one of the best local non-distributed SQL execution engine available today. We add very sophisticated distribution logic on top of that, and we pay a tremendous attention to the performance, which is essentially indices, and how do we keep indices and how do we process indices in Apache Ignite. So the end result is this dramatic performance increase. Again, it's a little bit unfair because Spark simply doesn't have indices, but even if you compare us with the other SQL engines, we're going to be 9 out of 10 times, we're going to be on top in terms of performance. So this is the kind of all I want to talk today and show you guys today. We're a little bit ahead of time, just by a few minutes. Once again, the last thing I want to show you is this little slide over here. By the way, thank you for attending this, and we're going to basically answer some of the questions right now. But you can always get, let me blow up this slide a little bit. You can always get this entire demo, by the way, on this GitHub URL. If you don't catch it, just look for Zeppelin demo on, just Google it and you'll find it. It's extremely easy to follow up. Literally, there's nothing there to do. You basically go to this GitHub page. You pull it down. There's a POM file. You open this POM file from Eclipse or IDE. Literally follow these little instructions: how to set up Spark and how to set up Zeppelin. And that's it. You literally just generate the JSON files, you load them up into the Spark, you load them up into the GridGain or Apache Ignite, and you run the queries. It's as simple as this, and you can play with this. So, Alyssa, back to you.
Great, thank you so much. Can you hear me okay?
Yep.
Okay, good. So the first question is, do we support complex data types? For example, arrays, structs, arrays of structs, nested structs?
Good question. Kind of caught me off guard. We definitely do, but maybe a little bit more sit-ups needs to be done on how to properly get them. That's a good question, as a matter of fact. You know what? The best way to answer this question, post this question or just ask this question on dev list on Apache Ignite. You're probably going to get a better answer with the code example right away. The answer is absolutely yes. The only kind of hesitation on my part is that I don't think we support it completely out of the box. You may need to convert some of the types. You may need to provide some little bit of code to support that. But definitely yes. But again, the best way, just pop this question on dev list in Apache Ignite. Like within a half an hour, you'll get the answer back with a specific answer.
Okay, the next question. Is there support for functions like hives, collect list, collect set, which are useful in aggregations?
Not out of the box, no. That's why we have our own custom SQL functions. If you want to write them, you can write them, but no, not directly.
Okay, is there support for Java 8?
Yes, we're fully Java 8 compatible. As a matter of fact, most of our API is Java 8. As a matter of fact, I don't think we support Java 7 as a source code. We can, we're in Java 8 fully.
Okay, so the next question is about, let's see here, it's about the demo. I'm not familiar with Zeppelin, but is there pre-caching occurring on the physical database server? Is there a difference between the first and second query on the database?
Well, Zeppelin doesn't do any precaching. Zeppelin is just the interface, right? So Zeppelin is just the UI. And that's just and the reason we use Zeppelin just to make sure we kind of showing you, from the same UI point. As far as the precaching, it really depends on implementation of Spark Ignite. None of us, I believe, do any precaching because maybe H2 engine on each individual node for Apache Ignite does a little bit of precaching, but I highly doubt this. I mean, it does, of course, some of it, but I highly doubt that affects the performance because we specifically in our implementation or our integration of H2, we instruct H2 not to do anything precaching because we are in-memory system. It will be kind of caching of caching. So everything you saw today and everything you can play yourself with this demo will be straight out, just literally call after call to a system. It will get a little bit faster naturally because there is some certain level of precaching happening, but it's not going to be dramatic, no. And the difference in performance would be pretty much the same.
Okay. Can you manage data distribution by logical key as Teradata primary index, for example?
Yes. One of the strongest parts of a data grid, and again, I can probably speak here for Ignite, not for Spark. For Spark is a little bit different. For Ignite, the data affinity, which is the proper term here, is one of the strongest part. You can basically define as your own affinity as much as you like, and not only you can not only can have a data affinity, you can have affinity between computations in the data, even outside the SQL context. By the way, if you want to run a traditional kind of MPP level processing, or any kind of HPC type of processing, high performance computing, you can collocate your compute jobs with a data sets these compute jobs require. And we have a strong support for affinity between compute jobs and data jobs, not only between just the data allocations itself. So yes, I do believe we have a probably more sophisticated support on this level than most of the systems in existence, because that's the core of what in-memory data grids and compute grids do, and that's a part of our fabric.
Okay. Do you support ORM on top of in-memory data fabric?
No, and we don't have to most of the time, because there isn't any impedance between like in traditional SQL world where you have a SQL table presentation and then object level presentation. And most of the time in memory data grids, you're dealing with objects. You store objects, you read objects. In terms of the SQL, the same story. Look at our example here. Let me actually pop up the slide deck so we can Look at this. Look at these examples. So the question mark here is, although it's a question mark here and here, it's actually going to be object. So you're going to get back an object. Object can be the binary object, which can be like a JSON-like presentation, which is schema-less, or it could be normal objects. So the need for or object relational mapping is almost non-existent in the data grids. You can still use it if you like it. I mean, if you happen to store a binary objects everywhere, you want to convert them to something else, but that's entirely your application-specific control. And most of the time, and it's one of the greatest advantages of a data grids as component of our fabric, is that you don't have to have an ORM. You deal with objects. Your keys are objects. Your values are objects. What you're processing are objects. What you get out of your SQL is objects too.
Okay, what are the memory specs of the machine on which the demo was done?
The demo was done on my MacBook Pro laptop. So, so it's a very simple laptop. It has 16 gigabyte of RAM. If you're asking about this demo, by the way, I'm not sure. Maybe you're asking about those billion transactions per second we've done, but that's different. This demo today, right now, I'm running it from my MacBook Pro.
Okay. Are indexes created on the data in off-heap memory? And does SQL query work better than the scan query on the data in off-heap memory?
Yes. So we can keep indices both on heap and off heap. I think we're moving. And by the way, this is actually a very interesting discussion we're going to have another day. We're actually moving most of our data storage to off-heap model because our blades, getting more and more RAM with every year. Today, you're buying a blade, you're unlikely to buy a blade with less than 64 gigabyte of RAM. And obviously, Java cannot support that. And there's no point of running multiple GVMs because you're basically going to get killed by thread context switching. So we try to catch up with this development, and we're trying to, a little bit re-architect what we do in terms of memory management, and we store more and more stuff in off-heap, basically where we fully control the RAM and we don't hit the garbage collection anymore. So that's a little bit kind of a detour, but yes, you can store indices, at least currently, both on-heap and off-heap. And as far as the performance of scan query versus SQL query will always outperform, always, unless we're talking about some kind of a very extreme use case where a small data set and whatnot. I hope I answered the question if I understood it correctly.
Okay. Does Spark support in-memory partitioning of data across computing engines?
I believe so, yes. I'm not a Spark expert per se, so you guys need to ask this question to the Spark community, but I believe so, yes.
Okay, well, that brings us to the end of, oh, wait, never mind. Somebody just came in last minute. We have time for a couple more questions. So if you do have questions, please go ahead and enter them in the GoToWebinar questions panel. Okay, do you have any advice or exact method for sizing GridGain cluster based on size of input data?
It's a good question, and we get this actually quite a lot when we talk to our users and customers, potential customers. That's one of the first questions. My immediate reaction, probably the best answer I can give it to you, try it. Measure it and try it, because we've seen a dramatic differences in how a particular data set lays out from disk to RAM, for example. Because objects on disk take different amount of space than in RAM, and just there's no exact science. If you're looking for an absolute back of a napkin estimate, I would say with the 2 replicas in RAM, essentially, if you want to have any kind of a fault tolerance, you have to keep data in RAM on more than one computer. If the computer goes down, you don't lose the data. So if you want to have that behavior, which is pretty standard, I would say you're looking for about 3x RAM requirement for the same data set you have on the disk. So if you have 100 gigabyte on the disk and you want to move this 100 gigabyte onto the RAM with 2 replicas for high availability and full tolerance, you probably need to have about 300 gigabyte, 3x of that in RAM across the cluster. Again, this is just the back of a napkin. Your use case can be different. I've seen use cases where RAM requires less memory than the disk for the same data set. But most of the time, it's about the same or slightly larger. Slightly larger, mostly because of the fault tolerance requirement. You want to, if you really care about this, if you want to have a fault tolerance or tolerance, you have to replicate your data at least into the one more computer. In case of the other computer goes down, you still have the data. So that's that's a kind of basic answer. But again, the best way, and I always keep saying, if you're serious about it, spend half a day and just load it up in RAM and measure it. It's just as simple as this. And most of the time, you can optimize it. You can basically play with this, and you get your results, exact results you're looking for your specific data set for your application.
Okay, we have a couple more questions. How do you compare with Exasol in-memory database?
Exasol, I don't think we, I don't think we run any tests against that at all. But again, if you're asking me about, just let me answer this question generally about in-memory databases. You'll be surprised, we do not really compete in any way, either as an open source project or as enterprise version GridGain. We don't, because there's a dramatic difference between database and a memory data fabric. Database predominantly is just a SQL engine. It could be in memory. There's plenty of them. MemSQL is a great one. If you just need essentially a SQL database that's in memory, there's plenty of options. But SQL databases don't do MapReduce. They don't do streaming. They don't do Spark integration. They don't do a Hadoop acceleration. They don't do file systems. They don't do HPC. They don't do many other things. And that's what's really cool about a fabric, is that it gives you a much more strategic view on a memory. It's not a single trick pony. Yes, we do have a SQL, but we also have a MapReduce. We also have a memory streaming. We also have a Spark integration with the shared RDDs. We also accelerate Hadoop if you need to. We also do complex clustering and service grids. So we do a lot of different things on Fabric. That's why we call ourselves a fabric, not a database, not a data grid. So, I'm pretty biased here naturally, and my bias towards a fabric, it's a more kind of canonical solution for in-memory processing. But if all you need is a SQL, and you need a little bit faster SQL, then SQL databases are a perfect choice.
Okay, and last question. Do you compress the data in memory? If so, what kind of compression ratios do you normally see?
We do not, and for a good reason. We thought about pretty hard, because some of our friends do that, and we believe that's not a right approach. The compression can be done much more effectively on application level, if you need to. Because keep in mind, when you compress the data, you have to decompress it every time you want to run a query against it. And that has an enormous penalty, performance-wise. So you're essentially trading capacity for a very significant penalty in performance-wise. And instead of doing it automatically, we basically decided a long time ago that we're going to leave it up to the application level. Compression can be done extremely simple. There's plenty of libraries. You can do it in one-liner. But you at application level can decide which and when and how you compress your particular data object before you store it. And you will be aware that you will not be able to query it easily. Because obviously, if you compress it, that becomes, just a byte store or byte blob, and you cannot really query inside of it. So it's a good question. I don't think there is, I don't believe our decision is absolutely 100% correct, but I believe, on a balance, I think it's a better approach than actually have a built-in compression capability into the product. because again, there's a plenty of libraries that can be done with one line of code. There's nothing else to do. There's no complexity there. But we believe it's better to be left for application developers who know precisely when, how to compress data before it's stored in data grid or in data fabric.
Okay, and this brings us to the top of the hour. If Nikita didn't get to your question, I will make sure that he gets a copy of all the questions, and he will either reach out to you or post a follow-up blog entry, blog post on our GridGain blog. I also wanted to just remind everyone that I will be sending a copy of the slides as well as a link to the recording, so you'll have those for your reference and to share. And with that said, Nikita, thank you for a great job. And audience,
Thanks a lot,
thank you
guys.
so much. Thank you very much. Please come to our future webinars. We have 3 new ones posted, and we're posting more every day. Thank you again, everyone.